Welcome, everyone. As chair of the physics department, it's my pleasure to welcome you to one of the highlights of our academic year, to the David M. Lee Historical Lecture in Physics. We've had many memorable lectures in past years, and I'm sure we're going to have another one today. And also today, we have the presentation of the Gertrude and Maurice Goldhofer Prize in Physics, awarded to outstanding graduate students. After the lecture, you're welcome to join us upstairs on the 4th floor in Jefferson 450 for a small reception with dessert and soft drinks. So there's various signs pointing you how to get up to the library on the 4th floor. Please remember to take all of your belongings with you because we will not be returning to this room. Okay, so now it's my pleasure to announce the Gertrude and Maurice Goldhofer Prize in Physics, which is awarded annually to outstanding theoretical and experimental graduate students in our department. Usually the prize is awarded to one outstanding experimental graduate student and one outstanding theoretical graduate student. This year, the pool of qualified students was exceptionally strong, and there was extra money in the pot. And after much discussion, the faculty of the department decided to award 4 prizes to 2 experimentalists and 2 theorists. All right, so I'm happy to announce the prizes. The 2 experimentalists are Anne Miao Wang. So, Anne. Then the other experimentalist is Harry J. Levine. So the theorist, the first theorist is Stephen Thomas Carr. And finally, we have George Obeid. I'd also like to take this occasion to recognize our Merit Prize winners. I don't have anything to give them, but they will separately receive the Merit Prize from the Faculty of Arts and Sciences. That's Trond Anderson. And Hofi Hanastotir. And now it's my pleasure to introduce Professor Arthur Jaffe, chair of the lecture committee, who will say a few words about the David M. Lee Historical Lectures in Physics. And welcome, Arthur.
When one mentions quantum theory, Erwin Schrödinger and
You can use that.
Yeah.
This is not on.
So Erwin Schrödinger and Vienna immediately come to mind, as does quantum entanglement. Entanglement serves as the basis for quantum communication. Professor Anton Zeilinger's experiments, they've shown that one can harness entanglement in the lab and implement quantum teleportation. This won him worldwide acclaim. So it's a great honor and pleasure to have Anton Zeilinger join us from Vienna to present the 2019 David M. Lee Historical Lecture. And I see the title slightly changed to Quantum Puzzles, from Quantum Foundations to Quantum Information and Quantum Communication. So this lecture has been supported since 2000 by the Marvin and Annette Lee Fund. It's given by distinguished speakers, and they speak on topics of interest to the physics community. I see there's quite a community here. Zeilinger has done incredible experiments revolving around the theme of entanglement. In 2016, his former student, Pan Jianwei, now at the University of Science and Technology in Hefei, finally took entanglement into space. He set out to test whether the Mochi satellite could entangle photons between Beijing and Vienna. This was successful. Zeilinger's name is also on the lips of every theoretical quantum physicist for the standard multi-particle generalization of the two-particle Bell state is known as GHZ. This was the work of Daniel Greenberger, Mike Horn, and Anton Zeilinger. Horn worked locally at Stonehill College in Easton and sadly died in January. So Anton Zeilinger is professor of physics at the University of Vienna. He's senior scientist at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences. He's no stranger to Massachusetts or to Cambridge. In 1977 to 78, he spent a year as a Fulbright Fellow working with Nobel Prize physicist Clifford Schell at MIT. He taught at MIT as visiting associate professor from 81 to 83, and he even had a part-time visiting position at Hampshire College for 6 years in the 1980s. As one might expect, many institutions awarded Zeilinger honors and prizes. For example, he received the initial Isaac Newton Medal from the Institute of Physics. That was in 2008. He received the Wolf Prize in 2010. And so many other prizes. If I were going to list them, I think the lecture could only start tomorrow. He was instrumental in the founding of the Institute of Science and Technology outside Vienna in Maria Gagin. He's a member of 8 honorary scientific societies, including being a foreign member of the US National Academy of Sciences. And he's currently president of the Austrian Academy of Science. Before Professor Zeilinger's lecture, let me now call on Professor Gerald Holton, who's originally also from Vienna, and Jerry will comment quite personally on Anton Zeilinger from a humanistic point of view. Professor Holton.
Thank you, Arthur, for your very thoughtful remarks. But we thought that something additional needs to be said for a couple of minutes. For in addition to being an extraordinary scientist, Anton Zeilinger is also president of the Austrian Akademie der Wissenschaften, as it is properly called, the Österreichische Akademie der Wissenschaften. Now, that is not well translated into an Academy of Science, because Wissenschaften means the whole spectrum of thoughtful things that may be studied. And therefore, it includes, under his energetic leadership, research, publication, promotion of 28 different research institutes, not only in the hard sciences, but also in the humanities, including history. Anton himself is also a humanist in the sense that he has a strong interest in human welfare and dignity. As one example, Anton has been deeply concerned about the human damage done by the Nazi government and its admirers when the Nazis brutally annexed Austria in 1938. Among the persons who then luckily managed to escape with their lives as children and going mostly to the US, some achieved something notable despite their very unpromising beginnings. Anton was moved by their life stories, and he commissioned a film. The film is called Exile and Excellence. The film presents interviews with 16 persons, such as Martin Kaplers, Lotte Behlen, and many others who are in this area, and who I believe plan to be at the showing of the film tomorrow, and I'll say something about that. The presentation of that film, plus comments by Anton, and a reception afterwards, will take place tomorrow, Thursday, at 4:30 at the nearby CES, which is the Center for European Studies in the Busch Zeilinger. It's open to the public. You're all invited to be at this film and to Anton's presentation of it tomorrow. That event is an example of Anton's deep interest to understand and act on human tragedies and on human achievements against great odds. With that, it's a great honor now to invite Professor Anton Zeilinger to give us his Lee lecture.
I should start. So, okay, I'm very grateful to be invited to this really distinguished lecture. And I hope that I find something interesting for every one of you. I'm very embarrassed by the two introductions. This is very kind and generous. Now, let me just set the stage for a moment about the situation which we have now. You all know that quantum physics started around 1900 with Max Planck, and certainly immediately afterwards with Albert Einstein. Then it took about 25 years to find the whole theory. And then something interesting in the from today's viewpoint happened, namely very soon discussions about the interpretation of quantum mechanics, which debate by many people. Most prominent is the debate between Bohr and Einstein about the meaning of the theory. And this is quite interesting because usually there are no discussions about the meaning of a theory. There is no discussion about the meaning of classical physics and so on. And at that time, many of these discussions focused around what the predictions are for individual quantum systems, which meant at the time that the workhorse were Gedanken experiments, thought experiments. Then due to technological progress since the 1970s, we have such experiments in various ways. Now they are abundant everywhere. And in the beginning, all these experiments, I would like to emphasize, were motivated by curiosity. Just philosophical curiosity. Is the theory really as strange as it predicts? And to the surprise of everyone in the field, beginning with the 90s, we had ideas that this might be useful for quantum for information, for quantum computation. The idea was communication, cryptography, and so on. And even these ideas in the early days were more or less, so to speak, academic. This has changed now. Now we have thousands of people working worldwide on this quantum information stuff, quantum computation. Nobody really knows yet how the future technology will really look like. And this slide I wrote a couple of years ago, and I predicted that around 2020 we have something new, ideas of a quantum internet or implementation of a quantum internet, which is really happening today. Albert Einstein is quite interesting in this respect. In 1905, with his famous predictions of particles of light, which were later called photons, it's the only of his papers he himself ever called very revolutionary. And so it's kind of quite the right thing that he got the Nobel Prize of 1921 in 1922 for that. There's an interesting statement by him: I want to spend the rest of my life thinking about the question what light is. It's quite interesting. Conceptually, it's quite interesting because we have learned in modern science that we stop worrying about what something is. We know how to describe it quantitatively and how to handle it. But the question of the essence is not uninteresting. This is something very interesting. It's a letter of recommendation for Einstein to be elected for the Prussian Academy of Sciences. It is signed by Planck, Nernst, Rubens, Warburg. Rubens was the person who did the black body radiation experiments by which Planck found his explanation. And it says the first part is not so interesting, that they recommend Einstein for the membership. And then it says, in the second half, I read it in English, the fact that in his speculations he occasionally overshoots the goal, shoot too far, as, for example, in his hypothesis of light quanta, should not be held too strongly against him, because without taking a risk occasionally, not even in the most exact natural scientists you can achieve something new. And the way I say this is because this was 1913. And he received the Nobel Prize of 1921 for exactly this idea. And that is one of the reasons why I like being a scientist. The whole community can change its opinion in the face of evidence. This is not possible in many other fields. Okay? Now, the idea of quantum information, the first idea, as far as I know, was Stephen Wiesner in 1970. He proposed the idea of uncopyable quantum money. He was not able to publish it for a long time. The idea simply was that the number, that there's some information printed on the bill. This is a bill, and I had an artist do this for me, where you have printed on something like polarization states of photons. This is very, very, futuristic. The point is that you can only read out these numbers. This is, horizontal polarization, vertical polarization, diagonal, anti-diagonal, or whatever. You can only read out these numbers if you know in which basis it was encoded. And this is something only a bank, for example, can keep as information, nobody else. This idea contains many of the basic concepts in quantum information. Contains the no-cloning theorem. It contains the randomness of the individual quantum events. It contains complementarity between different measurements, and it already contains the concept of mutually unbiased basis. The only concept it does not contain yet is entanglement. Here is the essence of randomness. I understand some people in the audience here are not physicists, not many, but some are, I understand. So a quintessential way to talk about the randomness is a half-silvered mirror, individual photon coming here, and you all know that the quantum state after the mirror is to be described as a superposition of the two possibilities, 0 and 1. The result upon measurement is completely random. And it is wrong to think that the photon was in one of the two beams before it was observed for various reasons. Now, this is one of the challenges. It's called the measurement problem. I will come back to this in the end again. John Bell required physics to explain why events happen, why specifically this detector fires or this one. The majority believes that there is no explanation, not even a hidden one. This animal is now today called a quantum or qubit, a notion which was introduced around 1995 by Ben Schumacher, who acknowledges a discussion with Bill Wouters where this notion was invented. A very interesting point is that already in 1909, and this, Einstein expressed in a meeting in Salzburg his discomfort about the randomness in quantum physics. This is really, really foresighted. There was no theory there yet. The quantum theory was not written down. He noticed that randomness is of a new qualitative nature in quantum mechanics and in classical physics. And in the letter of Max Born, he wrote this famous sentence that he believes that God does not play dice with the universe. He actually wrote that the old guy, the Alte, würfelt nicht mit dem Universum. So he had a very familiar relationship with God. Anyway, and supposedly this is now an urban legend. I didn't find any proof for this, but it sounds good. Supposedly Niels Bohr answered, "Stop telling the Lord how to run the world." I mean, Einstein is the only person who can dare to tell the Lord how to run the world, right? Now, just to show you one or two pictures from my home institution. This is the painting on the ceiling of our grand festive hall in Vienna, the Academy of Sciences. You see here Empress Maria Theresia in the middle, and so on, things like that. And here in the end, you have the four classical departments of the old university. This building was built in 1755 for the university. Our university was actually founded in 1365. It's the oldest still existing German-speaking, German language university in the world. Interesting point is, in this room, there was the first assembly of the students in the revolution of 1848. So imagine a revolution starting under such a ceiling, you know. The revolution was not successful, and in the end, the students were kicked out of the building, and we at the academy got to use it. The motto of the Department of Philosophy, Fakultät für Philosophie, is Causarum Investigatio, investigation of the causes. For the quantum event, we know that this doesn't work anymore for individual quantum events, which is quite interesting. Now here comes entanglement, already introduced in the introduction before. It goes back to this famous paper by Einstein, Podolsky and Rosen, though it is known now that Schrödinger had worried about these issues a couple of years before. This is a paper which was accepted by physical review without ever having been seen by a referee. It was just published like that. And when Einstein, when they started to send his papers to referees, he did not send them any papers anymore. He did not submit them anymore, which is actually a point. He said that the discussion between referee and author is a scientific discussion which should be out in the public. That's a very good point, actually. It's not so bad. Now, the notion is quite clear. You have these entangled systems where measurement on one implies a change of the quantum state of the whole system, which also implies a change of the quantum state on the other side. And Einstein didn't like this, as he also wrote in the letter, in the same letter I mentioned before with the randomness to Max Born. He talked about spooky action at a distance. This is what the New York Times wrote immediately afterwards. Einstein attacks quantum theory, and then it says scientist and two colleagues find it is not complete, and so on. So if you publish with Einstein, you are not a scientist anymore, right? Anyway, here is the development of our field seen in a different way. It's the number of citations the Einstein-Podolsky-Rosen paper received over the years, according to the Science Citation Index. It came out in 1935. There were very few citations in the beginning. I think it was in the first 2 years, it was only 5 citations, something like that. But of these, 3 were not so bad, because 2 were by Schrödinger, 1 was by Niels Bohr. So if you get quoted by 2 Nobel Prize winners, it's not so bad, right? But then nothing. The whole field was dead. The whole field working on the foundations of quantum mechanics did virtually not exist. It's actually quite interesting. Then in the 60s, we start up again because John Bell found out that the notion put forward in Einstein-Podolsky-Rosen, the worldview, I will say a little bit more about this, is in conflict with predictions of quantum mechanics. And then there's a virtual explosion around 2000, because entanglement against, to the complete surprise of everyone, turned out to be important in quantum information technologies. Today, the paper is by far the most often quoted paper by Einstein. It's quoted on the average once a day, which does not mean that it is read once a day. That's a different story. Schrödinger immediately captured the situation. He was in Cambridge at that time. He wrote that, no, he was not in Cambridge. He was published he was still in Graz. I would not call, namely, he coined the notion of entanglement and also Verschränkung, which is the German name. Here we go. Entanglement and Verschränkung is the German name, which is a much better name. Entanglement is like spaghetti, but Verschränkung is a well-defined connection, like my two arms here. And he said, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. That's quite interesting. He didn't, unfortunately, he didn't explain what the new lines of thoughts would be. Here is his grave in Alpbach in Tyrol. The equation is the famous Schrödinger equation, which is probably the most, also technologically and economically, the most important equation ever written down by anyone, if you think about modern high-tech and so on. This equation was actually written by Terry Rudolph on this thing. Terry Rudolph is a well-known quantum physicist at Imperial College in London and the grandson of Erwin Schrödinger. Now here comes, something is wrong here. Here comes John Bell, and where we basically discuss a situation where we have two photons created by a source. This is somehow quenched, I don't know why. Two photons created by a source, and they are created in this kind of state. Operationally, it means that whenever you measure the polarization of one photon, you find that the other photon has the same polarization, no matter in which basis you measure it. Now, this cannot be this cannot be explained by the assumption that the photons have their polarization before they are measured, because then you would not have this coherent superposition as seen here. Now, the achievement of John Bell was simply to show that, if you want to explain the correlations under two assumptions, namely, firstly, that the measurement result you get on one side is independent of what you decide on the other side to measure. This is the locality assumption, and the other assumption is that the measurement result reflects some local features here, some features of the apparatus which exist before and independent of observation. Then the strength of correlations is limited. It's limited particularly for, if you think about spin measurements, for measurement angles which are very close to parallel, but not completely parallel. What Einstein worried more is the following situation, that by measuring on one side, deciding what to measure on one side, you can predict with certainty what the result will be on the other side. And he argues in this as a famous volume, Albert Einstein, philosopher, scientist, with many interesting articles. He himself argues that, therefore, since the photon or the particle must have a well-defined state, according to him, the psi cannot describe the real factual situation. Here is the workhorse for our work for many years, production of entangled pairs of photons using nonlinear optical crystal, which is pumped with a UV pump. And if you arrange the optical axis of the crystal in the right way, then you can have the situation that one polarization is emitted along one cone, the other polarization emitted along another cone. And at the point, so this could be vertical, this could be horizontal polarization. At the lines of intersection of the two cones, the polarization is not well defined. It is not defined whether it's horizontal or vertical, but it is defined that the two have to be opposite. So this is entanglement. This is the essence of entanglement, besides a picture taken by Michael Reck and Paul Kwiat back at this time. A very simple way how this looks like in real life: a crystal pumped here, the photon pairs produced and fed into some fibers. This was actually a setup which we used at Documenta. We were invited for some reason to present our experiments at Documenta. Documenta is a famous exhibition of contemporary art happening every 5 years in Kassel in Germany. Really contemporary, so the artists have to be alive. That's one of the rules. No, I'm saying this because it's not the art between the wars or whatever, but it's really contemporary art. And we were invited to present 5 of our experiments, and we showed real experiments there, including a real Bell experiment. It's quite interesting, actually. This is the first proposal, actually, for the first experimental realization. Proposal was Eckert first with entanglement-based cryptography. The idea is simply, I try to explain it a little bit. A source produces a pair of photons, and then then what you can do is by manipulating only one of the 2 photons, you can change between 4 different kinds of entangled states, which you can then identify by looking at the statistics after a beam splitter. This is really unfortunate, but what can we do? These are the 4 maximally entangled states, which you in principle can distinguish. This procedure is called dense coding, or some people call it hyperdense coding, because you can encode more information by manipulating just one photon than you could do classically. Here is, again, something cut off, but it is not so important. I want to introduce one point now, which is important. Einstein, Podolsky, Rosen introduced elements of reality. They said, okay, since I can predict with certainty by doing a measurement here what the corresponding polarization on the other side must be, there must be an element of physical reality which corresponds to this observation. It's a sufficient criterion of reality, as Einstein, Podolsky, Rosen point out. It is not a necessary condition. Okay, and the interesting point is, if you now look at 3-particle correlations or more, you have this so-called GHZ states, which are named after these 3 authors. Greenberger, Horn was mentioned already. If you have an entanglement like this, three photons horizontally or vertically polarized in the superposition, then if you look at diagonal states, if you look at states which are not, if you call the basis where horizontal and vertical is the Z basis, if you look at X and Y basis, which are simply defined by sigma X and sigma Y operations on the individual beams, then the interesting situation happens that quantum mechanics predicts that the 3 results of X measurement should be +1. If you just use very simple algebra, but the local realist would predict that the product is -1. But just by multiplying these 3 equations here, this is the result of y, y, x, y, x, y, and so on. If you multiply this, you obtain this kind of result. So it is. So the point now is, and this is quite interesting from a fundamental point of view, and I think it hasn't been discussed enough yet conceptually, is that a consistent set of Einstein-Podolsky-Rosen elements of reality is not possible in such a situation, which is interesting because this set of elements of reality, namely the perfect correlations, are the basis of derivation of Bell's inequality for the two-particle situation. When we found this in the late 80s, I found it very surprising because it meant that quantum mechanics is that the contradiction between quantum mechanics and classical physics is not restricted to the probabilistic set of predictions, like in Bell's inequality. But it is also, there's also a contradiction when you have definitive predictions. Now, here's the result of the experiment. I should not go into details. The interesting point is that today, this kind of why did we get interested in this? Danny Greenberger, Mike Horn, and myself is quite interesting. Danny Greenberger came over to Vienna on a Fulbright fellowship. On the first day we sat together and we discussed what should we do. And we realized that everybody until this moment had only talked about entanglement of two particles. So we said, okay, let's sit down and calculate 3 particles. You know, it's not a very creative idea. It's it's just a silly step, you know. But it turned out to be extremely interesting. Now it is actually an entry in the physics abstract classification system and so on. These are the authors. One is missing here, Harald Weinfurter. This is Danny Greenberger. This is Mike Horn, who unfortunately recently passed away. He lived here, very close by. Here's Jian-Wei Pan. He was on the experiment. A co-author, Jian-Wei Pan, is now a big operator in China, as it was mentioned. He runs a huge enterprise, very successful. This is Dick Baumeister, who is in Santa Barbara and in Leiden. And this is Matthew Daniel, who was a graduate student, master student at that time on the experiment. Here comes teleportation. I was told that I should mention it, whatever it means. You all know why teleportation was invented in these films. It is a very capitalistic reason. It was to save production costs. Because it's easier to beam people up and down than to simulate a landing on a strange planet and all this. You know, it's much cheaper. So the basic idea is, and now I'm serious again, is that you take an object, an original, you scan out the information, you transfer the information which defines the object to some other location, and you reconstitute the object. Now, it was known that this is not possible because of Heisenberg's uncertainty relation. If you have only one quantum system, one system, not many copies, it's impossible to find the complete quantum state. Okay? So these people invented the Heisenberg compensator to fix that. There was a press conference at one time when Gene Roddenberry, one of the people on this thing, was asked, how does the Heisenberg compensator work? And his answer was, very well, thank you. Now the solution the solution is not quantum teleportation. This is an analog. I asked once the authors of the theoretical idea, I think it was Charlie Bennett or it was Bill Wouters, why they called it quantum teleportation. They said because they didn't come up with a better name. Basically, so here's the experiment which we did. Again, the same people. Now here's Manfred Eibel, another student on the experiment. And here is Harald Weinfurter, who was missing for some reason at the picture before. That's a picture drawn by a Scientific American magazine in an article which I wrote about quantum teleportation. Anyway, it says, here it says New York, what does it say? New York Quantum Transit Authority. No, this is just, this is just fun. This is not serious science. The basic point of the idea came out 1993. Bennett, Brassard, Crépeau, Joseph, Paris, Wouters. When this paper came out, my immediate reaction was, this is completely impossible in experiment. The idea simply is that you want to teleport this state here. You create an additional pair, an auxiliary pair, and then you project this one and one from the entangled pair onto an entangled state. And that means that this photon going out, or whatever it is projected on a well-defined state, which is related to the original by a unitary transformation, which is defined by which result you obtained in this projection on the Bell state measurement. One can simply imagine this as the Bell state measurement is a generalization of a spin measurement. In a spin measurement, you get plus or minus, up or down randomly if you have some unpolarized state. In a Bell state measurement, you get 4 results randomly if these two are not entangled with each other, which they are not. You get 4 states randomly, 4 maximal entangled states. I showed them to you before. And depending on what you get, you have to do a unitary transformation on the other side. There's an experiment on the Canary Islands done a while ago, where we do this teleportation, including feed forward of the classical results over a distance of 143 kilometers. Back then, the group of Jian Wei Pan did a similar experiment along a lake in China. And very recently, they were able to teleport a quantum state up from a ground station to the satellite, from a ground station which is located at an altitude of about 5,000 meters, because you want very little atmosphere between yourself and the satellite. Now, there's an interesting feature of these experiments. The question is, how do you project onto an entangled state here 2 photons? There comes an interesting feature. If you have 2 photons incident onto a 50-50 beam splitter, and if these two, you would expect simply, there are 2 possibilities. One is that either both photons are reflected. If you only look at the cases where you, either both photons are reflected or both are transmitted or both are reflected. Or basically, the amplitude for both transmitting and both reflecting, they extinguish each other. So this means something which is well known, that the 2 photons either come out both in one beam or both in the other beam. This is often also called the bunching of photons. Now, the interesting point is that there's one situation where this does not happen. I mentioned before that there are 4 Bell states. And of these 4 Bell states, 4 maximal entangled states, one is antisymmetric. If you, for example, consider this horizontal, this vertical polarization, is antisymmetric in this internal variable, which means that it is also antisymmetric in the spatial variable, which is not shown, so the total state is symmetric. And for this case, for this situation, it turns out that the 2 photons always end up in different outputs. So if you have 2 photons incident, and you get one here and one here, or 2 photons incident, you get one here, then you definitely know that they have been projected on one and only one Bell state. And that is very important, something we discovered about the time when we were working on trying to realize GHZ and Bell states. Here are the best maximal entangled states. A conceptually most interesting situation is entanglement swapping. So far, we had a situation that entanglement was created in pairs coming from one source. Does it always have to be the case that the two come from one source? The answer is no. Entanglement swapping is one such situation. You have two sources, each one producing a pair, and you use a beam splitter here, shown with glass fibers. That is just a technical detail. Beam splitter here, and you look only at the situations where you have the two detectors fire in coincidence here, one here and one here, okay? There are a lot of requirements about timing and so on, but this is not important, not an important details. So when you project these two onto when you get a coincidence here, then you know that you projected these two onto an entangled state, the incoming ones, a specific one, the antisymmetric one. Since this one was entangled with this one was entangled with that, it simply means that the outer two now become entangled. So you have two photons which share no common path whatsoever, no common past, nothing, and they suddenly become entangled, which is quite interesting. An even more interesting situation was proposed by Asher Perez. It was a famous quantum theoretician in Israel who unfortunately passed away already in 2001. He said, well, you can do the following. You have the two pairs of entangled particles, entangled photons, and you can decide, you bring one photon each together here, just as we said before, and you can decide here whether you project these two onto an entangled state, or whether you measure them separately, you measure the polarization separately. If you measure the polarization separately, it means that these two are not entangled, right? If you project them onto an entangled state, it means that these two are entangled. Fine, okay. But now he says, and this is the interesting point, now he says that you can make this decision here, what to do here, at a time after these outer two ones have been registered already. So you can decide after the registration of the individual photons, you can decide whether the quantum state you have to assign the system, I want to be very precise here, the quantum state you have to assign to the system is an entangled state, a mixture of entangled states, this state, this state, this state, or product states. Okay? Okay? Now, that's the argument by Perez, and the way we did the experiment a while ago is very simple. So how do you decide? The question is, how do you decide in the last instant whether you want to project these onto an entangled state or onto a product state? Is very simple. You could put in a beam splitter or take it out, but that cannot be done fast enough. So what you do is you build up an interferometer. So we create a pair of photons here, a pair of photons here. Oh, sorry. We create a pair of photons here and a pair of photons here. We measure the polarization of this photon instantly or very shortly after. We can manipulate here using half-wave plates and quarter-wave plates which polarization we measure. So anything on the Poincaré sphere. And here too, okay? We register this, and then we delay the other photon from each pair through a glass fiber of 104 meters, and then we send them through an interferometer. Now, this interferometer is the equivalent of a beam splitter which you put in or out, because if the phase shift within the interferometer is completely compensated, so this phase along here is the same as the phase along here. It's a well-balanced interferometer, which means that a photon coming here, a beam coming here, comes out here with 100% certainty because of constructive interference. Likewise, a photon coming in here comes out with 100% certainty here. So in that way, there is no beam splitter. In that way, you can find out whether the photon came from here or from here. You measure its properties by measuring the polarization. You project the two onto a non-entangled state. On the other hand, if the phase shift here is pi/2, 90 degrees, then what you get is an incoming beam here has the same amplitude to go out here and out here. Incoming here has same amplitude here and here. So which means that you project onto a superposition of the two, and that is just the equivalent of a beam splitter. You entangle them. Okay? And to show that the interpretation is correct, here's the result. The correlations in entanglement swapping, the correlations of these two photons in different bases, horizontal, vertical, right, left, circular polarized, or plus minus 45 degree. You have these correlations in all, if you do entanglement swapping in all three bases. If you project onto product states, you only can get correlation in one of the bases, which is shown here. Because that's the nature of entanglement, that you can get correlations in all of the bases. So in a sense, this is now we can now have a lot of philosophical discussions. In a sense, such experiments, and there are other experiments too, at least the way I see it is they show us that the individual events, the events which you record, are more fundamental than the quantum state. The quantum state are then the description which we make up to describe the situation. And the quantum state which we make up depends on the complete set of the experimental arrangement, something which we have learned from the Copenhagen interpretation a long time ago. Okay? So anyway, so much for entanglement swapping. Yeah, now this is just because I have to show it. I apologize. This is Schrödinger's cat. I don't want to say more, but if in the title we have puzzles, I should mention it. It's often said that the challenge is to see superpositions of dead and live cats. Well, actually what we have is massively entangled states, extremely massively entangled states. It's not just a superposition of one and another classical or whatever systems. The question still is, why do we see a classical world? And that's a different story, which I don't want to answer here. Now, there are various ways now, there are various developments going on now to go to larger quantum systems. One is look for larger objects, interference of larger molecules and so on, maybe someday even viruses or whatsoever. The other possibility is to go to higher dimensions. And here is, to go to higher dimensions, here is a case of a 3-particle state, which we decided to investigate a while ago, a GHZ state. Well, this is actually kind of embarrassing, but that's the way, when these states are known under these names, and it's quite embarrassing to be the author of, co-author of a paper which contains your name as a title, but that's the way it is. You have to suffer from time to time. Anyway, so the question is how to realize such a state. A state where now 0, 1, and 2 can be any 3 orthogonal states. How to realize such states, okay? We realized that recently experimentally. It was impossible for us to just sitting down and trying to find out how to design this to find a good solution. So we got some help. We got some help by Melvin, a computer program which designs quantum experiments for us. So what you do essentially is you ask Melvin to realize a certain quantum state. Then Melvin has various tools. You tell Melvin which tools he can use. And the interesting point is that Melvin comes up with solutions. I will show you one right away, which by human intuition we would not have found. If you look at this state, for example, this state is symmetric. You have particle 1, 2, 3, and each one defined in 0, 1, and 2. So you would expect naively, or I would have expected naively, that the final experimental setup has to reflect somehow the symmetry of the state. No, completely wrong. Melvin found a solution which is very economical and absolutely not reflecting the symmetry of the state. And as such, you will see it, that I have to run through with my finger, and I convince myself it does the right thing, but the next morning I forgot it again, and I have to run my finger through again. This is really human, and intuition is, at least my intuition is very limited. Well, an important tool is the question, how do we go to higher dimensions, particularly with photons? There are two ways. One is by using different propagation modes, like you could imagine glass fibers coupled different modes. You know, one you call 0, the other one you call 1, the third one you call 2. And the more elegant method is to use what's called orbital angular momentum states, which interestingly were not part of physics, with a few exceptions, until 1995, when Han Wordman and colleagues found them classically. The situation is actually basically very simple. Instead of a plane wavefront, you imagine that the wavefront you're talking about has a spiral symmetry, spiral wavefronts. And if you go to quantum mechanics, you can have different pitches of the spiral, which means that an individual photon can carry 1, 2, 3, or 4 units of h bar, you name it. Here's again what Melvin does. Here are the tools that he can use, and the question about how to realize. And the realized situation is rather involved, rather complicated. I should not go into details here. This would be a talk in its own right. I skip this now, it's not so important. Another success of Melvin is the discovery of a new way how to create entangled states. And that is, if these are, suppose these are crystals, these crystals we are talking about, these are the pairs of photons produced. We are not, this is very simplified, we are not showing the pump and so on. And what you now do is you feed the beams in one, created by one of the crystals back into the back of the second crystal. So when you have a photon here, you don't know whether it was created here or whether it was created here. When you have a photon here, you don't know whether it was created here or here, and so on. And that way, you can obtain a scalable way to produce entangled states with arbitrary number of photons and arbitrary dimensions, which is quite interesting for the future. Now I come to the end. Just some nice recent result. I go back to Bell's inequality. I go back to testing whether this entanglement really exists. One of the assumptions in all these experiments is that you have to assume that the choices done on both sides are independent and random. About random, we can talk for a long time, but it really has to be random, but the two choices have to be independent of each other. How can you guarantee that? Well, in principle, I mean, in many of the experiments, one used quantum random number generators to set the polarizer, or whatever you name it, independently on both sides. But in principle, you could have something which influenced both random number generators in a way which you don't know. So the solution was proposed by these three people. One of them is here in the audience, or at least one of them is in the audience. Maybe the other one is also in the audience. Sorry? Only one. Are you sure? Okay. So the idea was to use as distant sources of randomness as possible. And it turns out, at least from a reasonable point of view, these are quasars. You take the fluctuations of quasar light, two different quasars at two different ends of the universe, if the universe has ends, I don't know. And you take the fluctuations of the quasars to determine to determine the polarization setting. In the real experiment, that is the paper which was just published recently. Another co-author is also in the audience, Alan Guth. Where is he? Here. So we have 3 co-authors of that paper in the audience now. The experiment, I just show you how the experiment was done. We are on the Canary island of La Palma. There are 2 telescopes. One is the Telescopio Nazionale Galileo, Italian telescope. And the other one is the William Herschel telescope. Both telescopes have a diameter of 4 meters. And you look far out, look at distant quasars. Then, in addition, you produce here in this small container, that telescope is not used. In this container, you create pairs of entangled photons, send 1 photon down here, 1 photon down here, and some property of the starlight decides which feature is being measured. The property of the starlight being used is actually the color, slight fluctuations of the color above an arbitrary chosen cutoff edge. I'm running out of time, so I have to be. I don't have to go into the details here. This is not so important. That's the setup where the source is. And one morning, the setup looked like this. There was a storm on the Canary Islands, and it turned over the container. And after that, inside, this was the source, and there was big gap, and so everything was kaput. Actually, it turned out that the only thing which was really broken was the crystal producing the entangled photons. The rest was put up back together very soon. Here is the Italian telescope. It's very beautiful, elegant Italian design. It's really nice. That's the receiving station. It's not so important. Here is the random number generator, the cosmic random number generator, the starlight coming down here. Here's a dichroic mirror with some bandpass filters. Blue light goes to one detector, red light to the other one, and fluctuations determine which polarization is being measured. Here is the William Herschel telescope on the other end. So this is an experiment really combines the cosmic with the small scale. Here's a picture of the backward line cones of the observation event here, and for the 2 furthest out objects, which one? No, in terms of look back time, we are talking about 12.2 gigayears and 7.8 gigayears, and we obtain a nice violation. We looked at 2 pairs of photons, 2 pairs of galaxies, 2 pairs of quasars. We get in both cases significant violation of a Bell-type inequality. So that means that even if so it simply rules out any reasonable overlap of the causes for most of the observable universe. Now, just to run through a few other entertaining pictures. One is this quantum key distribution using the Chinese satellite Mitzius, which was launched now nearly 3 years ago. In China, I was there when the launching happened. It was quite interesting. I should mention one thing. This satellite was, I mean, I had planned in Europe for a long time to have such a satellite, and I tried to convince authorities and so on. I was not successful because the decision processes are so complicated in Europe. I don't know how it is here in the United States. But in China, it happened that one day my former student, Jian-Wei Pan, called me up, and he said, we are now putting up this satellite. Do you want to collaborate? And I said, well, what is your time scale? He said, 5 years. Well, very ambitious. How much money do you have? $100 million, but that is just a number. Okay. And they really succeeded. I can talk about them it's quite interesting why they succeeded. And it turned out that the satellite works extremely well. They did all kinds of experiments using this kind of satellite. Here's the orbit of the satellite. The satellite orbit is chosen such that it goes through the nearly exactly to the poles, and it's stationary with respect to the sun. So that simply means that the Earth rotates underneath, and on every place on Earth you have at least one passage during the night. So it can cover everything in the night. So here's the passage. Here's the passage, for example, here's Xinglong Station near Beijing is one of the stations used. This is another Chinese station in western Tibet. And here's our station in Graz, which we use. Here, but that's not important. This is also not important. That is a picture of what you see. There's the satellite track. What happens is that from this we send up from the receiving station we send up a red laser light, and as soon as the satellite receives it, it sends back green light, and that way they can lock onto each other, and in the end the quantum states are exchanged. Here's a small picture, but it's the same. It contains the same information as we had before, but it might be interesting to see it move. So you should come to Graz so you can see. Now we have, now it works. It didn't work when we showed it before. So this is always a finite exposure, right? So you see it, so you see this green track of the satellite. This was used to have an encrypted video call. Here's the president of the Chinese Academy of Sciences, where we basically exchanged the key in the encryption standard using this quantum technology. We also had a one-time paired transmission of two images, Schrödinger from Austria to China, Mitzius from China, Schrödinger from Austria to China, and Mitzius from China to Austria. I should not go into too many details here. Now, about the future. In China, they are planning to put up a couple of satellites within the next 6 to 8 years. A network of low Earth orbit satellites and also geostationary satellites, and connect them to local networks on the ground, fiber networks on the ground. Okay. We are planning in Austria to have fiber networks on the ground. Here's Vienna, connecting different capitals. That explains the name here. Different capitals in Europe, using entangled-based system in quantum cryptography, and also connect this to satellites. Now, in the end, just in 1 minute, a fun experiment which we did. We means a large international collaboration. This is a list of authors, which is kind of getting towards where some author lists in particle physics are. But these are 12 different laboratories in the world. The idea was to have, so the main work was coordinated, the main work was the coordinating work, planning work, and everything was done by the group of Morgan Mitchell at ICFO in Barcelona. The idea is to have human choices, to have humans who put in random numbers through an app. You could download an app, put in random numbers. These random numbers were then sent via a cloud to individual laboratories. And in these laboratories, they set randomly the polarizers or whatever the variable is, okay? So that way we had 100,000 human participants, 12 laboratories on 5 continents. And there were about, how many was it? I forgot the number now. 97 million binary choices during that experiment. The assumption is that human decisions are random and independent. So in the end, I come to a few provocative statements. I quote Bohr here. When in 1948, to me, this is a very important statement. However far the quantum phenomena transcend the scope of classical physical explanation, the account of all evidence must be expressed in classical terms in the end. Okay? Now, coming from Vienna, I cannot avoid showing you my personal position. If we allow in physics only concepts which can be operationally realized, then I would claim that it is operationally impossible to discriminate between what it says here, reality and information. There is no way. Okay? So from that point, okay, then what is the quantum state? Many of the puzzles are, as I mentioned, are related to the taking the quantum state as too real, the quantum state being something propagating out there. Okay, from that perspective, the quantum state is just a representation of information, namely of which information? It's information about results of observation of the apparatus which you got before. So it is features of the classical apparatus. Every measurement result is a feature of a classical apparatus. So it represents classical information. And what is it good for? It is good to calculate probabilities of future measurement results, which is again features of classical apparatus. And I would suggest that there's no need for more. This is enough. We don't need more than that. There's a beautiful statement by Heisenberg. The act of recording, namely the measurement, is not a physical, but rather, so to say, a mathematical process. With a sudden change of our knowledge, also the mathematical representation of our knowledge undergoes, of course, a sudden change. That's the reduction. That's the quantum measurement problem. There is no quantum measurement problem. It would be silly not to change the representation of our knowledge, namely the quantum state, when we get new information, namely a measurement result. But here's one point I conclude now with two statements. One is by Rabi. I'm probably the only one who wrote this down. There was a conference in 1985 here in Cambridge at the American Academy of Arts and Sciences. It was a centennial conference for Niels Bohr. And Rabi said there, I think we are missing a very basic point about the interpretation of quantum mechanics. The next generation, when they found it, will knock on their heads and say, how could they have missed that? Now, we are already quite some time after that. And here's my final slide, very famous by Einstein. I want to know how God created this world. I'm not interested in this or that phenomenon. I want to know his thoughts. The rest are details. Thank you very much for your attention. I ran over a little bit.
We have time for questions before we go to the library.
Do you have any thoughts on how God created the world?
Sorry?
Do you have any thoughts on how God created the world?
No, no. But I'm working on it.
My question is, there is this big dichotomy between quantum mechanics and relativity. One has to do with space and time, and the other has to do with the quantum world. And they are not compatible. So the question is it classical to be requiring your physics to occur in space and time?
That's a very good question, yeah. There's one observation is very interesting. If you look at multi-particle entanglement, okay, then the measurement results and the correlations are independent, completely independent of the arrangement of your apparatus of the space-time arrangement of your apparatus. So in some sense, it seems as if these quantum correlations are deeper than space and time.
Any other questions? Maybe from a student. Yes, Aris.
Thanks for the great lecture. So what do you see as the most important challenges that we need to address for kind of scaling these things, this quantum communication, quantum internet up, both experimentally and theoretically?
If we talk about quantum communication, I would say will certainly happen with photons. There's no other way. Right. And there, the limit are the detectors and the sources. The limit is the best quantum communication links you can have now are about this, typically the size of a city. And we talk, if we are optimistic, about megabits per second, something like that. Even less, 100 kilobits or what, which is nothing compared to the modern internet. And the limitations are high power sources for individual quanta and fast enough detectors. With detectors, we actually better now than with sources. But this is something I also told people in industry, that they should put money into these two questions. The fundamental concepts have been proven and they work.
Okay, maybe one more question. All right. Well, so then I take this opportunity to thank Professor Zeilinger again for a wonderful lecture.